So now in this video we're going to quickly go over the NPN switch. In the last video we looked at the gain of a 2N2222 NPN bipolar junction transistor. We have the meter set to measure milliamps. I know it's less than 20 milliamps, so I have it in that setting. Otherwise I would put it to 200 milliamps and make sure it was below 20 milliamps at first. But in any case, we are going to just quickly review that with this 100,000 ohm resistor. I'll move it up here. We will complete the circuit. So this is going to the base, the middle pin of the NPN transistor. The emitter is down here. And now going through the resistor, the meter, and the base to emitter, we have 0.05 milliamps of current. And let's lower the setting of this a little bit to 2 milliamps, and we get a more accurate reading. So actually it was 0.044 milliamps. So now we got to set this back up to 20 milliamps or less, because that amount of current going through the base to emitter, last video we saw that the transistor amplifies that current, this particular one, by about 257 times, about that. So without a load, and if I get a good connection, oh, that's right, we have to add the resistor over here. Now the current is flowing through there. Before it was flowing through the meter. That was the problem. So I'll leave that in there because while you're doing these test measurements, it's easy to overlook that kind of stuff. So there you can see now, this is probably about 257 times, in that range, the current that was going base to emitter. And it holds steady even if we have the resistor there. And the LED is probably going to throw it off just a tiny bit, but we'll have about the same amount of current if we put the LED also in series. There you can see now it's a little less than 11, but it's holding somewhat close. So that kind of throws off the voltage, making it to the transistor, which will affect it a little bit. So now we're going to zoom in to make modifications to this circuit to make it a switch. There is a 220 ohm resistor here. Last video I did, it was a 100 ohm resistor, if you saw that video. So that's one change I made so far, plus adding the LED. So now we looked at the transistor while it was in the active region. So if you remove the base current, it is cut off. It's not going to conduct. And then if you apply current to the base region so that it limits current, it's what's limiting current through something else, then it is in the active region. We want to saturate this transistor. So we saw the current that we got with the 100,000 ohm resistor, about 11, just to make the math easy, 11 milliamps of current. So we're going to pop that out of there and grab a 10 kilo ohm resistor. Also, to make this a little bit better, we will yank that jumper out and we'll grab a switch. So we'll put the switch where the base of the transistor is. You can see one pin is there. The other pin to the right is up up 2 rows. So it's not connected to the collector, it's up one more. So it's getting a little crowded there, but I don't think it's too bad. Now we're going to take a 10 kilo ohm resistor and attach that there. So it's a 10 kilo ohm resistor, and so we'll have about 10 times the current to the base, which would be close to about half of a milliamp, which would not light an LED very bright. In fact, we can look at that. We can take this here and put that to the switch, and when I close the switch, you can see that's how bright this LED, which actually doesn't do too bad, lights at half of a milliamp of current. But instead, we're going to get the resistor to the switch, and you see this a lot in the demonstration circuit. An actual circuit, you'll just be using a signal from another electrical circuit that is weak for whatever reason, too weak to light the LED as much as you want. Instead, we're going to use a resistor to limit the current. And now the transistor will let probably around 100 milliamps of current. That's too much though for the LED. So now the resistor is what is limiting the current, not the switch. The switch is just taking that signal coming in, and we can consider this fully on because it's conducting a lot more than what the load needs, and now the load is limiting the current. And we can see, we can measure the current going through the load. And also with this transistor, we could probably safely measure the current without the load at the 200 milliamp setting. So we are at 20 milliamps, and I think it's going to be about 15 milliamps based on the resistor and the LED voltage drop. So okay, 13 milliamps of current. And now let's this is a little risky, but I'm going to set the meter to measure 200 milliamps, and we'll see what the transistor will let through without a resistor. So I'm going to go to the positive rail there, and if it's beeping, we went over for some reason. That's right, I got to press the switch now. And there you can see about 100 milliamps of current, and now it's warming up. Now you can see why if this was if this transistor was only rated for 100 milliamps of current, even though that's kind of what we calculated, and we didn't calculate carefully, we just quickly estimated. You can see it's rapidly rising as it heats up. So that's one thing about the switch. You avoid that problem. The current is set by the load. So now, as we kept talking about, you got to be really careful measuring current. You don't want to accidentally measure a power source current because it outputs more current, especially this power source will output more than 200 milliamps of current. So you want to make sure when you're done, you put the meter back to measuring voltage, both there and where the red probe is. But in any case, in summary, because I mostly was focused on the demonstrations right now, but when the transistor is used as a switch, in this case the NPN transistor, you want it to go from two states, either fully conducting or not conducting at all. So right now it's not conducting at all because this switch is open, and so no current is flowing. When I close the switch, now a small amount of current can flow through the resistor, the switch, and then the transistor, the base to emitter. That's allowing a lot more current to flow from collector to emitter. And since we're using this as a switch, we either want it off or we want it to conduct a lot better than what the load is going to need. That way the load can set the current. All we're doing is either turning this on or off. Otherwise, it's not affecting the current through the load, which is what we are worried about. So that's what makes a bipolar junction transistor, in this case an NPN type, a switch, whether it is fully off or fully on, and it's controlled by a weaker signal, usually another part of a circuit. But for demonstration purposes, it's easier to understand what's going on with a switch. Just realize, with the mechanical switch, just realize if you see an NPN, bipolar junction transistor, in a circuit as a switch, there'll be another part of a circuit, another complete circuit that is connected to it, maybe through a resistor, maybe not, and it is sending a weak signal that it wants to turn something on, but that signal is not strong enough, so you just plop in the transistor and it takes care of that for you. So thanks for watching, and I will see you in the next video.